On January 12th of 1888, one could have been forgiven for thinking that when the day dawned, it was going to be like many other cold but manageable days on the central plains of the United States. A week before, a storm had dropped a few inches of light, powdery snow that had not melted due to the seasonably cold temperatures, but this was in no way out of the ordinary. As school children were bundled up and sent off to local one-room schoolhouses to continue the lessons they had begun after the Christmas break, no one had any idea that there was developing a storm system that would bring catastrophe across the region. The schoolhouse blizzard of that day developed and moved with a rapidity that had been unexpected. Ahead of the cold front that was diving down out of Canada, relatively warm air was pulled up into the northern plains, with morning temperatures reaching a relatively balmy 28 degrees Fahrenheit. Due to this, people didn't bother to listen to the short-term forecast that called for the advance of a heavy squall line that would occur later in the day. Though it should be mentioned that the forecast did not predict an event that was as severe as would happen. With the warmer weather, people took advantage of the break from the usually brutal cold to get out and take care of the various chores that they had neglected over the last few weeks, in places like barns, fields, and chicken coops. Yet, at about 3 p.m. across the Central Plains, conditions began to deteriorate rapidly. Within an hour, not only did 6 inches of additional snow fall, wind began to blow with an unprecedented ferocity. This created whiteout conditions within minutes. More deadly, however, was the fact that behind the front came brutally cold air. Within an hour, temperatures dropped over 40 degrees Fahrenheit, with wind chill factors reaching minus 60. Those caught away from their homes were in grave peril. This included many school children ready to be released from schools to walk home. All across the plains, men, women, and children struggled to survive in the rapidly worsening conditions. 235 of them wouldn't make it. Many died only a few feet from the relative safety of their front doors, unable to see or hear those calling out to them to lead them home. It is hard for us, I think, to imagine such an occurrence today. If you're like me, you have at your fingertips an up-to-date characterization of the weather conditions in your region. You know when severe weather is about to hit through a well-developed alert system that is able to keep you apprised when conditions are worsening dramatically. More than this, however, you know well ahead of time if such conditions are likely to take place. With 3, 5, and 7-day forecasts available from the National Weather Service or from any number of private forecasting enterprises such as the Weather Channel, I at least know days in advance when a severe thunderstorm outbreak might take place here in Georgia, or whether or not a tropical storm will threaten my relatives that live along the Gulf Coast. This knowledge and information is available to me and to you through a hidden infrastructure of data gathering and analysis apparatus that is able to measure the state of the Earth's atmosphere and, with remarkable accuracy given the complexity of the system, predict what it will do. This last week, I had a chance to get a look at how that hidden infrastructure is created and how it does what it does as part of a NASA social event. And in this episode of the Scientific Odyssey, I like to share what I have learned with you. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. The Scientific Odyssey Unscripted, Weather Forecasting, and the JPSS Polar Orbiting Satellites. This podcast is another of our occasional Odyssey Unscripted episodes where we take a break from the narrative of our usual story due to some sort of a special event. In this case, the event isn't something specific, like the landing of a space probe or the announcement of some monumentous scientific discovery, but rather more of a report about a gathering of scientists and engineers to discuss the upcoming deployment of a really important scientific instrument. The event was the joint NASA-NOAA social event to discuss and publicize the JPSS, or Joint Polar Satellite System, with participation from all of the science and engineering partners, including Ball Aerospace, United Launch Assembly, Raytheon, Northrop Grumman, and others, along with the project managers from NASA and NOAA. Now, before we go too much further, I need to warn you about what will likely be the rampant overuse of acronyms. This is just something that gets really hard to avoid. I'll try to keep them to a minimum, but it's hard to eliminate them completely due to the fact that so many of the things that we'll be discussing have such incredibly long and descriptive names. So for those who may not know, NASA, or the National Aeronautics and Space Administration, is the U.S. government agency tasked with facilitating the nation's activities surrounding the exploration of space, including all scientific activities associated with that endeavor. NOAA stands for the National Oceanographic and Atmospheric Administration, and it is the U.S. governmental agency responsible for scientific activities associated with characterizing the Earth's oceans and atmosphere, along with other things. Since we're going to be talking about satellite-based science in this episode, we'll be discussing both of these agencies to some degree. NASA for the space and aeronautics bits, and NOAA for the atmospheric and oceanographic sciences. As we've said, we'll also be talking about a program that goes by JPSS, or Joint Polar Satellite System. So when I mention JPSS, what I'm really talking about is a series of satellites that will be launched over the course of the next couple of decades that will have specific characteristics and a specific set of mission parameters that we'll explain in some detail as the show goes on. One more confession is in order before we continue. While I'm calling this episode quote-unquote unscripted, the truth is that I've done a lot of scripting on this episode because there's really a lot of details I want to make sure I include that I get right, that I do correctly. Therefore, while there will likely be a bit of ad-libbing going on, as is usually the case in these kinds of shows, I've done a lot to outline this episode to make sure that I say what I want to say. While some of that will come from some of the materials the social events participants, myself included, were provided, much of it comes from the interviews, presentations, and panel sessions we got to participate in on June 19th, 2017 at the NOAA Center in Boulder, Colorado. So let's set the stage here just a bit. In talking about these satellites, the project manager for Ball Aerospace, Alex Chernushin, made a really great point that these things represent part of the United States' infrastructure and, as the lead-in hopefully made clear, a really important part of that infrastructure. When most of us get up in the morning and go through our various routines, I expect that a part of that is to check the weather forecast. Maybe you want to know the weather and whether you need to carry an umbrella, or how you might want to dress, or if traffic will be delayed due to adverse conditions or something along those lines. Maybe you're planning a getaway vacation or some sort of a trip, and you want to know what to expect at your destination if you decide to travel. Maybe you're involved in an activity that relies on a specific set of weather conditions in order to proceed with success, something like a sporting event, for example. In all of these cases, an accurate forecast of the weather conditions can be helpful or even necessary. In other cases, on the other hand, such a forecast can actually be a matter of life and death. Here in the southeastern United States, hurricane season has begun, and we've had two tropical systems moving through the waters to the south of us. One that came ashore near the Texas-Louisiana border, bringing extremely heavy rainfall to the area of the Gulf Coast and, regrettably, causing significant flooding in the Atlanta metropolitan area. As another example of the high-stakes nature of weather forecasting, one of the participants at the NASA Social, Mr. Carl Jones, works for a private company who provides forecasting products throughout a number of states to governmental agencies who need to know whether to deploy snowplows in the case of severe winter storm conditions, as well as give advice on what actions those institutions or entities will need to take that will mitigate any sort of worsening road conditions. Mr. Jones's forecasts help guide states across the Great Plains and Midwest in deciding whether to close roads and interstate highways, as well as to how to best deploy those resources they have to keep transportation flowing. As a third example, the National Weather Service office in Boulder, one of 127 such regional forecasting stations across the United States, provides up-to-the-moment wind forecasts for the Denver International Airport. DIA, as it is known, is situated in a challenging wind environment, and in order to keep aircraft traffic moving in a safe and efficient manner, the FAA, or Federal Aviation Administration, works with the local National Weather Service office to shift flight plans to best accommodate takeoffs and landings as the winds shift. Without this cooperation and collaboration, it is likely that the airport would reliably land 140 aircraft an hour, and so air traffic would back up not only in Denver, but ripple out across the flight networks over North America. For the 1/3 of you or so who are listening to this podcast from places outside the United States, I can assure you that similar efforts are taking place in whatever agencies are tasked with weather forecasting in your neck of the woods. No matter if these services are provided by national governments or by private organizations, the ability to forecast or predict the condition of the Earth's atmosphere at a given place and time is a matter of great convenience, economic viability, and, at times, life and death. So, how do these forecasts happen? And by the way here, to be clear, I'm going to use the term forecast throughout the episode when it comes to weather, but what we're really talking about here is a scientific prediction. In this case, what's being predicted is the state of the atmosphere at some time in the future, usually in a particular locality. To make this prediction, one has to have something they use to make it from, what we might call a hypothesis or a model. For most of human history, these hypotheses were based on previous experience. If a farmer saw a particular progression of cloud types over the course of the day, he could predict that there would be rain in the next morning based on his experience of that having occurred in the past, when he'd observed such a progression previously. Now, of course, there are all sorts of problems with this kind of approach, as personal experience is often subject to things like selection and confirmation bias. But such observations were often collected in things like almanacs, often in the form of easy-to-remember aphorisms familiar to those who sailed the high seas or worked the lands. More deliberate efforts to characterize these sorts of things took a while to get going, with organized efforts not really getting traction until after the Civil War in the United States. One of the reasons for this, I think, has to do with the fact that dealing with the atmosphere as a system is a tremendously complex thing. By comparison, astronomy, the subject we've been studying for the last 18 months or so, is pretty darn simple, or at least regular in terms of its behavior. I'll talk a bit more about this idea of complexity later on in the episode. In time, organized measurement of the state of the Earth's atmosphere did come together, facilitated by the development of technologies like the telegraph and telephone, in order to gather data over a wide area and collate it to form a coherent picture both in space and across time. With this, one could not just see the state of the atmosphere at the surface of the Earth, but also how that atmosphere changed over time in an organized, or at least understandable, set of patterns. By the way, if there's one theme that I hope will emerge from this discussion, it's how much the entire endeavor of weather forecasting has grown as more and more data has become available. Forecasting in this era that we're talking about here is what we might now call trend casting. By looking at how things were and how they might have changed over the last little bit of time, a trend could be determined, and that trend would be used to forecast the weather. Unfortunately, since the forces that drove atmospheric motion were broadly unknown, these forecasts were usually very inadequate when it came to predicting what might happen in dynamic situations, such as the development of severe weather situations such as thunderstorms or, unfortunately, the rapidly developing winter storm we talked about in the introduction. With the development of aviation and radio, it became possible over time to develop a vertical profile of the atmosphere, and with organization, this data gathering could be synced up so that the state of the atmosphere over a very broad area, i.e. on a continental level, was possible. During World War I, an understanding developed regarding the movement of large air masses dominated by specific atmospheric conditions, such as being cold and moist or warm and dry. While the forces that moved these air masses was still poorly understood, it was realized that much of the weather took place along the boundaries of these air masses, called fronts, in a borrowing of military terminology from the armies that clashed across the European continent of the time. These improvements led to concurrent improvements in trend casting and in determining where severe weather might actually break out. As aircraft technology improved and planes could reach higher altitudes, more data came in, and during World War II, the great bombers flying missions across the Pacific discovered great rivers of air near a boundary of the atmosphere that we now call jet streams. These jet streams not only moved air masses, but they also delineated regions of colder and warmer air, as well as areas of high and low pressure. This, too, led to better forecasting. The greatest improvement that came out of World War II, however, was the development of rocketry. While first used, of course, for weapons systems, it wasn't long before individuals realized that being able to put objects into permanent orbit around the Earth would have an enormous benefit in many areas, such as communication. As such, it wasn't long before someone suggested putting a camera on a satellite, boosting it into an orbit that was geosynchronous, and having it take pictures of the atmosphere. While meteorologists were skeptical about the utility of such a system at first, being deeply ensconced in surface observation methods, the launch of the first geostationary Earth-orbiting satellite, or GOES, quickly changed their minds. Up until that point, they were really trying to study a very complex system from inside of that system with all of the limitations that came with that. The ability to look down on the system from the outside of it, when combined with all of the other data taken from the surface, revolutionized meteorology. Now, meteorologists could see where their models and hypotheses had correctly predicted atmospheric behavior on a large scale and where it had missed. In those early days of satellite-based meteorology, it was not uncommon for a researcher to recognize that their forecast had completely missed the development of a weather system that, due to gaps in the surface-based data taking, mainly occurring over the oceans, had caused things not to show up in their models. The other development that began during this post-war period was the dual development of digital computing technologies and algorithmic mathematical problem-solving methods that would give rise to a revolution in computer modeling. John von Neumann, often known as the father of the modern digital computer, is said to have developed the first computers and programming languages, namely Fortran, in order to do weather forecasting. These two technological developments would allow for the laws of physics governing fluid dynamics and heat transfer to be coded into a computer program that would be able to simulate the evolution of the atmosphere over time. These mathematical models would take the atmosphere over a region, say North America, and impose a mathematical grid both horizontally and vertically. At as many of the grid points as possible, the data gathered at surface observing sites, by weather balloons, and in time by satellites would be assigned in order to sort of initialize the model. Once this was done, the model would then apply the various forces dictated by the encoded physical laws and move the atmosphere around, at least in a simulated way. Early on, these models were fairly crude and pretty inaccurate, but by comparing the model outputs with what was observed to actually take place, they were improved pretty rapidly. As computing power increased, models were improved and data taking became more precise and accurate. Models were either tweaked to give results in better agreement with actual conditions, or were replaced with new models that better took into account all of the physics taking place. These models have now reached the point where they provide reliable guidance of what weather conditions will be like, not just for a day or two in advance, but for at least 5 days and often a week into the future. It is a truly remarkable achievement in not only understanding, but also in being able to predictively model a really complex and chaotic, and I do use that word in its full mathematical sense, system. Okay, so now that I laid a bit of a foundation, let's start moving towards talking about the JPSS program. And I should note here, what I've just given you is really just a tiny taste of the long and interesting history of meteorology and forecasting. If we ever get to that point of our 5-year mission, as it were, characterizing and understanding the Earth's atmosphere is one of the quote-unquote big questions I hope to treat in a whole lot of detail down the road a little bit. So, if I left out some piece of the story that you feel is really important to know more about, rest assured that I'll eventually get to it. It's just sort of outside of the scope of this episode and what we're going to try to talk about. So back to the subject at hand. The Joint Polar Satellite System, or JPSS, is a series of weather satellites known as polar orbiting satellites. As I said in that overview, the GOES systems are satellites that sit in what are known as geostationary or geosynchronous orbits. What that means is that they're at an altitude of about 35,786 kilometers above the Earth's surface. And that gives them an orbital period that is exactly the same as the Earth's rotational period. This means that they take the same 23 hours, 56 minutes, and 4 seconds to make one orbit that the Earth needs to rotate once on its axis. And so the satellite sits above the same position above the Earth. These are the satellites that take those glorious pictures of the disk of the Earth and show the movement of the clouds over the course of time. For those of you who live in hurricane-prone areas like I do, these are the satellites that allow us to track the path of those monstrous storms in real time. NOAA generally operates 2 of these GOES satellites at any given time. Both are in orbits above the Earth's equator, one each for the east and west coast of the North American continent, with a view that spreads well across the landmass in one direction and into the ocean in the other. As powerful as these satellites and instruments they carry are, they do have some pretty significant limitations. The first is that due to having to be in these very high orbits, they're a long ways away from the thing they're taking data of. The very breadth of their view limits the precision and accuracy of the data they can take. The second limitation is that since the Earth curves away from the GOES systems at the poles, parallax effects really limit the accuracy of the data they can take at above 60 degrees north latitude in the northern hemisphere and below 60 degrees south latitude in the southern hemisphere. As we will see, these limitations can have a significant effect on the models that use the data they provide. Now, before I move on, there are 2 additional points of interest I'd like to mention. The first is that the next generation of GOES satellites is just recently been launched. The first of these satellites, known as GOES-R, has been positioned over the middle of the North American continent for calibration and testing of its instrumentation by the research teams at both NASA and NOAA. However, as I understand it, it is likely that the satellite will be turned over to the operational forecasting folks this week in anticipation of it being moved either to the GOES East or GOES West positions to take place of the satellite that's already there. This satellite represents a huge upgrade in data taking capacity and capability, both in the precision of the data, but also in the download speed. something that will allow meteorologists to get literally up-to-the-minute data on developing storm systems. The second point I need to make goes to a mistake I made in an earlier episode of the podcast. Faithful listener Neville Young pointed out to me that while I had said that GPS satellites were in a geostationary orbit, this is not actually true. The network of GPS satellites is actually in a somewhat lower orbit at around 22,000 kilometers, and thus the entire network moves with respect to the Earth's surfaces. It is this motion that gives GPS systems some of the functionality we take for granted. I want to apologize for that mistake, and I want to give a big thanks to Neville for setting me straight on that account. So, now we're finally ready to talk about these polar orbiting satellites and systems such as the JPSS. Polar orbiting satellites supplement the GOES satellites by operating at a much lower altitude in a completely different orbital configuration. When launched, the JPSS satellites are going to be placed in an orbit that is about 824 kilometers above the Earth's surface, so that they travel in a circle that goes over both the North and then the South Pole. We'll post a graphic of this kind of orbit at the podcast website, thescientificodyssey.typepad.com. But one way to imagine it would be to think of the Earth as some sort of a piece of fruit, like an orange, and that the satellite is as a fruit fly that goes over the top where the hole for the stem is and then circles down the side of the orange to fly across the bottom and then comes back up to the top again. Now, as the satellite travels along the sort of almost, but not quite, longitude line of the Earth, it takes data of the condition of the atmosphere underneath it in a wide swath. At the altitude that it is at, it takes about 90 minutes for the satellite to make one complete orbit. In that time, the Earth turns about 22 degrees, and so the next time the satellite comes around, it's looking at a slightly different stripe of the Earth. This means that it can measure the entire atmosphere of the Earth every 12 hours. What I hope you can see is that this is a really good complement to the GOES system, in that though it can't show you the atmosphere in real time all of the time, it gets the same level of data of the entire atmosphere, including the regions of the poles. And since it's so much closer to the atmosphere, it can get data in much better resolution. How important is this data? Well, 85% of the data that is fed into the models that lead to weather forecasts actually comes from the polar orbiting satellites rather than from the GOES satellites. In fact, one of the stories I heard at the social told of an experimental research team with the European Union's meteorological offices that did their big hurricane prediction model. For those who remember Hurricane Sandy, which came ashore in 2011 along the northeast coast of the United States, the European model was one of the first and most consistent in predicting that the storm would make a westerly turn and come ashore rather than doing the usual recurve path that took it harmlessly out into the Atlantic Ocean. This prediction, soon picked up by most of the other models, allowed emergency management personnel to make advanced preparations for what was a significant weather event causing billions of dollars in damage. The interesting thing was that after the landfall, researchers there in Europe reran all of their models, but instead of running them the way they were, they ran them without the data from the polar orbiting satellite systems and the information that those things provided. What they found when they did this cool little piece of research was that their model completely missed the development of the blocking high pressure system in the northern Atlantic that ended up pushing the storm ashore on the Atlantic seaboard. Without all of that polar orbiting satellite data, the models all would have been wrong and the damage and loss of life would have been catastrophically worse. So, as is the case with the GOES systems, NOAA generally operates a polar orbiting system with two satellites orbiting opposite each other, one on each side of the Earth in a sense, giving complete data scans every 6 hours to feed into the various computer models. These are operated in conjunction with similar systems from the European Union's METSAT agency as well as the Japanese Space Agency, or JAXA, bringing the total number of sets of data to a once every 3 hour frequency. For NOAA, the JPSS system is scheduled to become the next generation of satellites in the long line of such systems. With a total of 5 satellites that either have already been launched or will be launched once every 5 to 7 years on a schedule in order to assure that there'll always be 2 satellites in orbit, given things like design life, this whole project promises to really revolutionize what we're doing with our weather forecasting. After the break, we'll look at the development of the program, the design and building of a satellite of this type, and what instruments will fly on each of the satellites and what kind of data they'll take. So let's talk about the development timeline for a satellite system. From what I've been able to research, the JPSS program grew out of a couple of different programs that had initially been developed during the early 2000s. One for NOAA and another for the Department of Defense. As program review was undertaken, it was determined that there was enough program overlap in some areas and enough diversity in others that the missions on the weather data side could be combined. And so, in 2007, a new initiative was undertaken that would lead to the JPSS program that would make data available to a very wide number of users, while the more specific defense programs would go to another sort of satellite system that was more suited to those needs. As such, the joint NASA-NOAA program would take advantage of technologies developed for that earlier program, but on a framework and implementation similar to previous polar orbiting systems. The JPSS-1 satellite is about the size of a typical American SUV with the mass of, say, 8,500 kilograms, and the development of the vehicle underwent several stages. As you can probably imagine, you can't just throw something like a weather satellite together with off-the-shelf parts, even what might be thought of as off-the-shelf parts for the aerospace industry. The first thing that has to happen is what is known as the requirements formulation stage. In this initial process, the various stakeholders come together and determine what specification the vehicle needs to meet. This includes desired capabilities, i.e., what will the satellite be able to do, necessary systems such as propulsion, navigation, and communication, and standards and protocols for the data formats. From this, the initial plans are created that determine what instruments will fly on the vehicle and how data will be collected, transmitted, and shared. This stage of the process occurs in 2 distinct phases. The first is the design phase, and the second is known as procurement. This second stage is where the bids are put out for the design of the spacecraft as well as the instruments. In the case of JPSS-1, the first satellite of this series, the general spacecraft contractor was Ball Aerospace, which was also contracted to design and construct the ozone measuring instrument that we'll discuss a little bit later on. Raytheon Corporation was selected for the construction of the visible and infrared camera. Northrop Grumman was selected for a couple of other instruments, and ULA was selected to provide the launch vehicle, which turns out to be a Delta II rocket. Once this process is completed, construction begins. This takes place really in 2 parallel tracks. On one side, there is the construction of what is known as, quote-unquote, the bus, in aerospace vehicle parlance. The most straightforward way to think of this is that the bus is the superstructure of the vehicle. It's initially the framework to which all of the other things will get attached, and then the wiring that allows for data transmission, spacecraft propulsion, communication, and navigation. The other track of this whole process is instrument design, manufacturing, and testing. In this, each instrument is given dimensions into which it must fit from the original design and specifications. The manufacturer then subcontracts out the design of the various electronics and optical components according to the specification it has to meet. Each of these subsystems have to meet an incredibly rigorous set of specifications that go above most of the terrestrial requirements. This is known as aerospace grade. One of the things that has to be done is that all of the electronics have to be significantly hardened in order to withstand the much higher levels of high energy particles such as fast protons they will encounter in their operational environment of flying through the Earth's north and south magnetic fields 14 times a day as the spacecraft passes over the poles. This requires that circuitry be both shielded and redundant. Once these processes are completed, the instruments are then integrated into the vehicle at the Ball Aerospace facility in Boulder, Colorado, with initial testing of the data taking and communication happening there. Once this is completed, a full vehicle testing process commences. At the time of the NASA social, the vehicle was undergoing the last of these tests, and so unfortunately we weren't able to actually see the thing. So what kind of testing gets done when you go through this whole suite of tests? The first test is a vibrational test. The launch of the vehicle is really going to shake it around, and so it's necessary to make sure that all the spacecraft systems are all up to the rigors of that kind of an environment. This is basically done using a really huge set of loudspeakers that are borrowed from, say, touring rock bands, believe it or not. The testing takes place along all three axes with vibrational profiles modeled on data taken from previous Delta II launches. The next test, which is related to this first one, is an acoustic test, and it's done in much the same way, in order to simulate what the vehicle will be subjected to by being inside the Delta II's launch cone. Launching a rocket generates an awful lot of noise, and the vehicle and the instruments have to be able to survive that. The third kind of test is an electronic interference test. Here the satellite is placed inside what amounts to a huge Faraday cage that shields it from all outside interference of an electromagnetic nature. In this environment, the various systems' ability to talk with each other and not cross-talk with other systems is tested. During this time, the spacecraft is also subjected to levels of radiation it will experience in space to make sure that there are no obvious part failures due to this. The final test is what is known as a thermal vacuum test, where the spacecraft is placed in conditions as similar to its lower Earth orbital environment as possible. The goal is to make sure that the various components will end up running at about the 65-degree Fahrenheit range, with thermal blankets being used for those components that will be exposed to the cold of space that don't produce very much power, and radiator cooling systems used for those that do produce a lot of heat. The spacecraft is kept in this environment for about 2 months and run through a gamut of different temperatures to make sure that the systems are all robust. For those who are interested, the power on the vehicle is produced by a single set of solar panels that stick off kind of to one side that can produce all of the energy necessary for the spacecraft's function in conjunction with storing energy in batteries to run the instruments when the vehicle passes through the Earth's shadow. The total energy requirements when everything is turned on is a meager 1600 watts, a little more than a typical microwave uses in its highest power mode. Think of that the next time you're heating up a cup of water for a really nice hot cup of tea. The energy that microwave is producing is about what it takes to power a typical polar orbiting satellite. Once these tests are finished, the vehicle is packaged up and delivered to Vandenberg Air Force Base out in California, where it will be launched at night, hopefully on or around September 21st if everything goes well. If that launch is successful, as we should expect given the Delta II's amazing reliability record, the satellite will go through a period of testing and calibration before it's designated as NOAA 20. I'll talk about the calibration process in some detail when I get to discussing the instruments in a bit, but before we do that, let's take a look at the program on a more macro scale level. The JPSS program was established in 2011 during the Obama administration following the successful flight of a vehicle known as Suomi NPP. Named for James Suomi, a meteorologist I believe at the University of Washington. This initial program was something between a technology's prototype and a beta test for the systems integration NOAA was interested in using in its next generation of polar orbiting satellites. The vehicle achieved all of its flight goals so well that it was actually transitioned to become an operational vehicle, replacing a previous NOAA instrument platform. On the Suomi NPP spacecraft were prototypes of all of the instruments that will fly aboard the JPSS spacecraft over the next 20 or so years, and each has performed rather admirably. One of the questions I got to ask the systems managers regarding the test was what they learned and modified as a result of the Suomi mission. The first thing they learned is that they just really had a really good design. The platform worked well in producing good data and communicating through the satellite to ground downlink with the various information going into the forecasting models really well. Additionally, it was found that the various instruments gave vastly enhanced arrays of products to researchers and forecasters that had really been previously unavailable. So it really was a remarkably successful test. However, with that being said, as with any beta test, there were some issues discovered with the platform that had to be solved with the JPSS systems. The most notable of these was the need to have an instant switching of data lines in the vehicle itself. In the case of a momentary failure, such redundancy prevents the systems from having to perform a full reboot, which leads, of course, to a loss of data collection capabilities. Thus, having a sort of what you might call an A and a B channel that can be switched between the two very quickly provides an extra level of reliability, and this was implemented. Another improvement in the JPSS vehicles was a double set of telemetry antennas. One antenna that communicated with the ground, and another that communicates with an orbital network of satellites to allow for greater coordination with other vehicles in the data-taking network. While atmospheric data is communicated through the vehicle's high-gain antenna twice a day at receiving stations in Finland and Antarctica, there is still a need to transmit navigational and systems information. This is done through a separate channel and now can take place through two different pathways, again increasing reliability. The JPSS program, as I mentioned earlier, calls for a total of 4 vehicles to be deployed over the course of many years. While different contractors will build each vehicle due to timeline constraints, each will be designed and built to identical specifications to both save on costs and provide a stable and comparable data platform for the next 2 decades. Over the course of the program, there will always be 2 polar orbiting satellites deployed. But due to operating life limitations, it will be necessary to replace vehicles every 5 to 7 years or so. This is done to ensure that a vehicle does not suffer a catastrophic failure near the end of its lifetime, leading to an increase in the amount of orbital debris that is becoming a bigger and bigger issue. Put another way, if a vehicle, say, is determined to have a full operational life of 7 years, this is really a determination of how long it is thought that the spacecraft has a high percentage chance, 95% for example, of operating without having some sort of a massive failure to, say, its propulsion or navigation systems that would compromise the structural integrity of the vehicle. It may be that actually the vehicle could operate somewhere up to, say, 10 or 15 years, but the chance of failure might then increase from, say, 5% to 25%. And if the failure were to occur, there's a reasonable chance that parts of the spacecraft would be flung into other orbits that could endanger other operational vehicles, such as, say, the International Space Station. Therefore, it is prudent and actually required by international treaty to deorbit the vehicle after its replacement has been launched and verified, so that there's not a chance of that sort of thing happening. In any case, the JPSS program is really set up to provide high-quality atmospheric and oceanographic data for the next generation of researchers and forecasters. So, as a capstone to this episode, what I'd like to do is talk a little bit about each of the instruments. There are 5 packages that will take data on the spacecraft. 2 that will gather the nuts and bolts atmospheric data, 1 that will take very high quality images of the Earth's surface, and 2 that will provide data for climatological and atmospheric research. Let's look at each of these in turn. The first 2 instruments are what are known as sounders in meteorological terms. What they do is look down into the vertical column of the atmosphere and they gather information about temperature, moisture content, and atmospheric motion. A good way to think of this is to imagine the satellite over a portion of the Atlantic Ocean, say a region between the coasts of Africa and South America, just north of the equator, where tropical waves can pick up that first bit of spin due to the Coriolis effect that might turn them into tropical systems in the summer. Each instrument, which is a camera really, looks down into the box as it is the Earth's atmosphere. And you can think of this box as being divided into a grid with layers stacked on top of each other. What each instrument does is use a different frequency of light in its spectral band to look at the light coming from each layer of each grid cell. Using a sophisticated set of algorithms, atmospheric scientists can determine the relevant data regarding the grid cell at each of the various layers. This is repeated for each grid cell very rapidly. The two instruments are called the Cross-Track Infrared Sounder, or CrIS as its acronym form, and the ATMS, or Advanced Technology Microwave Sounder. While CrIS has a much better resolution due to the fact that infrared light has much shorter wavelengths than microwaves do, it suffers from the problem that it actually can't look through clouds. The microwave sounder, on the other hand, is able to do that, and so the two instruments are actually really good complements to each other. Both instruments allow for measurements of the chemistry taking place in the atmosphere, as well as measurements of the concentration of CO2. Data from the instruments will be used in a vast variety of ways. One of the first of these is one we've already touched on, and that is weather forecasting. The numbers the instruments gather are really state-of-the-art ways of looking into the state of the atmosphere, and these are rapidly fed into the computer models. These are computer models such as the High Resolution Rapid Research Model, or VIIRS model, and the GFS model. And these are used to do both, or to do not just both, but all sorts of short, medium, and long-range forecasting. Basically, when you go out to your National Weather Service or Weather Channel forecast to get hourly or 3 or 5 and now 7-day forecasts, these are really strongly guided by the computer models that use the data gathered by these instruments. One question I had regarding these instruments is how they actually get calibrated. How is the spectral data that they take turned into real numbers that get fed into the models? One way in which that happens is through comparing the data with that taken by weather launches, or I should say weather balloon launches, at many locations. Another is to take data using aircraft that are specifically equipped with instruments for just that purpose. Both NOAA and NASA operate a fleet of aircraft whose mission, among other things, is to provide additional data for the calibration of these satellite instruments. One such project has a DC-9 aircraft that is flying from low altitudes to high altitudes and back again. The plane sort of porpoises its way from pole to pole along a latitude line in order to give the vertical resolution of these measurements. And again, we're measuring things like temperature, moisture content in the atmosphere, and atmospheric motion. And these are used to ensure that the data from the satellite instruments is valid and accurate. On the research side, these two instruments on the spacecraft allow atmospheric researchers to more fully characterize what is known as the hydrologic cycle. This is the process through which water goes from evaporation to atmospheric transport, i.e. the water vapor turns into clouds, those clouds get moved around, to precipitation, to surface transport through rivers or groundwater or whatnot, back to some larger body of water, and then evaporation again. This also helps understand how heat energy is moved around the globe in water vapor and winds. In the longer term, these sorts of efforts will support the goal of more fully understanding long-term atmospheric and oceanic cycles such as El Niño Southern Oscillation in the Pacific and the Julian Oscillation in the Atlantic. In short, these two instruments are the heart of the JPSS mission, and the meteorological workhorses gathering the data that makes the level of weather forecasting we see today actually possible. And I know that some of you are listening to this, and you're likely rolling your eyes as it seems that meteorologists actually get this sort of thing wrong a lot. If you look at it, though, they actually do a really pretty good job, especially when compared to just 50 years ago. In the 1960s, you'd be lucky to get a 3-day forecast with any level of accuracy. One day was about all we could do. and it was all we could do with any sort of accuracy above what we called that trend casting idea. We can now match that sort of forecastability at the 7-day level, with 5-day forecasts being really very good. Do the forecasts miss sometimes? Well, of course they do. The atmosphere is a really complicated, chaotic system that sometimes does things, especially at the boundaries of air masses, that can be kind of hard to predict. Nevertheless, the chances of someone getting caught in a snowstorm and dying on the way from the barn or out to the mailbox are pretty much non-existent now, and that's a pretty impressive improvement. The next instrument I want to talk about is known as the VIIRS, or Visible Infrared Imaging Radiometer Suite. By the way, from that name you can sort of see why we want to use an acronym like VIIRS, right? That's just a mouthful. This thing is the high-resolution telescope camera combination on the JPSS spacecraft that will be able to take exceptionally good pictures of the Earth's surface. It can quote-unquote see and measure things like vegetation and its changes in growth, dust, pollen in the atmosphere, aerosols, and other pollutants. It can look at forest fire plumes. It can measure ice and snow. Whatever you can think of that it might be able to see and measure, you can name that. When they showed us the various products that the different instruments could deliver, and they, by the way, were showing us data from the SUMI NPP version of this instrument, the VIIRS was far and away the largest type or number of different products that can be delivered. The data allows for researchers to see a huge number of physical interactions between the Earth's surface, its oceans, and its atmosphere, all important to understanding how things actually are changing. One of the most striking ways to visualize all of this data is something known as quote-unquote science on sphere, and that's an actual term. You can Google search on that. This is actually a projection system. You actually sit in a dark room and they've got this great big sphere that's about 8 or so feet large, and they project from 4 different projectors onto the sphere the data in a way that is easily visualized, and it makes many of the relationships that you want to take a look at really, really obvious. Many science museums and educational institutions have invested in one of these, and so if you live near one, I would heartily recommend finding some time to visit it to see what a really tremendously powerful tool it is. Again, the name of the thing, and you can Google this, is Science on Sphere. As an example of how this data can be used, one of the things many international air quality treaties now ban is the wholesale burning of flammable waste products from, say, oil wells or refineries. Such activities put an enormous number of really hazardous pollutants into the atmosphere, as well as release incredible amounts of greenhouse gases. The VIIRS camera can easily detect such activities, allowing international monitoring agencies to notify the appropriate authorities to impose the needed fines and tariffs on those nations that participate. While this data is probably of lesser importance, at least directly to forecasters, the VIIRS instrument provides researchers in many other areas a valuable tool to observe the changes in the atmosphere and ocean with an unprecedented level of detail. This brings us to the 2 instruments that are actually primarily research focused. The first of these is known as the Ozone Mapper Profiler Suite, or OMPS or OMPS. As the name suggests, this is the instrument that measures ozone levels and concentrations in the atmosphere. It does this in a couple of ways. One method is known as the limb observation method, where the instrument looks through the atmosphere at an oblique angle and measures the amount of light that is absorbed in the ultraviolet portion of the spectrum by ozone in the stratosphere. This has been the workhorse method for the last few generations of satellite-borne instruments and has provided a good, if somewhat indirect, method of making measurements. OMPS, however, has a second way of determining ozone concentrations, and that is with what is known as a nadir measurer. Nadir, if you may recall from early episodes of the series, is the Arabic word for down or below. And what the instrument is able to do is look straight down from the satellite and measure concentrations of ozones at several levels in much the same way as the sounders do. This allows for a much, much higher resolution picture, say on the order of 8 by 8 kilometers in the square, that is about a kilometer thick. Something that represents a huge leap forward in being able to determine concentrations on a really fine grain scale. One of the most interesting things I got to do while in Boulder is to visit the lab of Patrick Collis and Chance Sterling of the Ozone and Water Vapor Group. These two scientists are continuing an ozone research project that has been going on for about the last 40 years, using what I would think of as really nuts and bolts hardware. The idea is a really cool one, where a small instrument has been developed and built that carries two chemicals into the atmosphere on a balloon-mounted radiosonde. The chemicals, potassium and iodine, undergo a chemical reaction that is catalyzed or made possible when there is an ozone molecule present. This reaction produces two electrons that can then be routed through an ammeter in a simple circuit. By measuring the current in the circuit, the instrument is able to make a surprisingly precise measurement of the ozone at whatever altitude that radiosonde is at. What happens is that about once every week, a balloon, and we can think of it here as just a typical big weather balloon, with this ozone instrument radiosonde attached to it, is released from about 8 different places around the world. Places like Boulder, Colorado, and Hilo, Hawaii, and Fiji, and a number of other places. The balloon ascends at a rate of about 5 meters per second, and the circuit is able to report ozone concentrations at a rate of once per second. This data is radioed back to the ground station by the sonde, giving a really high resolution profile of atmospheric ozone concentrations from the launch point up to an altitude of about 100 kilometers, which is about where the balloon will actually expand so much that it bursts. The radiosonde then parachutes back to the surface, and it transmits data while it does so, which gives you data on the way up and on the way back down. All of this data is used to calibrate the satellite readings of these kinds of instruments like the OMPS. One of the really cool things about visiting the lab is that both Patrick and Sterling had a real passion and enjoyment of the work that they were doing. You could tell by talking to them that these guys were really what, I might call lab jockeys. Some scientists are theorists who are comfortable with working with equations and mathematical models. They're doing things with pencil and paper. They're really thinking about abstract ideas. Other guys, or other scientists I should say, people like me anyway, really get into using those mathematical models to explore the behavior of systems using computer simulation techniques, where the behavior of the systems can be studied by tweaking parameters in the model and then seeing what happens and seeing if that matches what really took place in the real world. On the other hand, researchers like Patrick and Sterling love the hands-on aspect of building things and being in the field. You could see the energy and excitement in their eyes as they talked about working through solving the various problems that come up and getting the instruments working. For them, the real-world data collected by the clever and creative equipment their hands have built represent the heart of scientific inquiry. And you could tell these guys were the kind of guys who really love to tinker with the physical apparatus that takes the data. For them, going out into the field and launching a weather balloon and looking at the data as it came back was just really the height of their scientific work. One of the things, by the way, that Sterling has done with this project is pretty cool. He's attached a number of different kinds of cameras to the sondes as they've been launched, and he has taken a number of breathtaking high-altitude photographs from the very edge of space itself. If you've ever seen the coffee table book that shows those things, Sterling's the guy that produced that. He's a scientist doing actual ozone work, and he's found a way to integrate sort of his artistic side into doing that scientific work, and it's really just absolutely fantastic. The final instrument we'll talk about is what is known as the CERES, or Clouds and Earth's Radiant Energy System instrument. The purpose of this research instrument is to more completely characterize what is known as the Earth's solar energy budget. Every day the Earth receives a certain amount of energy from the sun. Some of that energy is reflected by the upper atmosphere, some of it is reflected by clouds, some of it is reflected by materials on the surface such as snow and light-colored sand. The rest is absorbed at any number of levels, though most of that absorption is actually done at the surface. This energy is then radiated in the infrared part of the spectrum as dictated by the various laws we've discussed in early episodes related to black body radiation. Some of this is then absorbed or reflected back to the surface by various atmospheric phenomena, most notably clouds. This produces what is known as the greenhouse effect that keeps the surface of our planet warmer than it would otherwise be. The CERES instrument will allow for the study of these phenomena in order to more fully understand the role of various agents, such as clouds. We know that clouds do two things. They reflect incoming visible light back into space, something that would cool the atmosphere, and they trap outgoing infrared light from the surface, a process that should warm the atmosphere. One of the early big climatological questions is which of these processes had a greater effect. Are clouds net coolers or net warmers of the atmosphere? Which of those two processes was more dominant? The scientific evidence to date suggests very strongly that clouds are really net coolers, but the exact amount is still somewhat unknown. The CERES instrument will help to answer this question. That in turn will further improve forecasting and climate change models by more accurately taking into account the effects of these kinds of things in how atmospheric energy is modified by the presence of things like clouds. Similar measurements will be made to more accurately quantify the effects of things like snow, spreading urban environments with greater amounts of blacktop, and the process of desertification due to increased grazing of livestock and destructive farming practices. As I hope you can get a sense of, the JPSS-1 satellite and its similarly equipped follow-on vehicles are extraordinary scientific platforms that will give meteorologists, atmospheric scientists, climatologists, and oceanographers, not to mention geologists and a host of other research groups, a powerful set of tools from which to gather enormous quantities of high-quality data. This data will refine forecasts, inform models, and improve our understanding of the processes that shape our lives and our world, from the state and change of the atmosphere on multiple timescales to the interaction of the ocean and the sky. It's a remarkable time to be involved in these fields of research, and I truly believe that anyone thinking about it will find that this is really an exciting area in which to engage and participate. As I conclude this episode, let me give this week's shout out and thanks to the NASA Social Program for giving me the opportunity to learn more about the work being done in these areas. While I've been familiar with some of the efforts in their earlier iterations, the one-day visit to the NOAA Boulder facility has really broadened my horizon. Thanks also to the scientists, researchers, program managers, and engineers involved in the JPSS program from NASA, NOAA, Ball Aerospace, Raytheon, Northrop Grumman, and ULA for taking the time to explain your work to a diverse group of interested parties. Finally, to everyone I got a chance to meet over the course of the day, it was truly a pleasure to get to chat with you about your work, your interests, and your passions. You inspired me. If you, my listeners, are interested in participating in a NASA social event, I'd really encourage you to apply. There are a couple of different places you can get information, but the easiest thing to do is follow NASA Social on Twitter or just Google the term. They're having events all over the place and across a wide spectrum of different sorts of ideas and projects and who knows what. And it's a great way to learn more about what's going on. For my overseas listeners, I'm afraid I don't know of similar programs in other countries. But if someone wants to drop me a line, either on our Facebook page, at my Twitter account, which is, by the way, at Chad Davies, all lowercase, or at cldavies@mac.com, I'll be happy to pass the word on to others. Seriously, Let me know what kinds of things are out there for folks to get involved in, whether those be scientific agencies and organizations and their public outreach efforts, things going on at local science and natural history museums, or just something your local skywatching club or science cafe might be doing. Let me know, and I'll do what I can to get the word out through whatever various channels I have. Also, while it may take me a bit of time, I'll post a bunch of links to different resources about the JPSS program and the work being done at NOAA Boulder to our website, thescientificodyssey.typepad.com, for you to check out if you want to know more. I've really only scratched the surface of the science being done with this, and there's a ton more to learn about if you're interested. Next week, we'll head back into the narrative by looking at the remarkable work of Henrietta Leavitt and others on variable stars, something that will prove to be key in our understanding of our place in the universe. Until then, full sails on your journey.